In this two-part video series, you'll learn about univariate or one-variable summaries. In this first video, we'll focus on visual summaries. Consider some context. Bike sharing is becoming a more popular means of transportation in many cities. Shown here is a snippet of data from the Capital Bike Share service in the Washington, D.C. area. Each row here represents a different day, and the variables measured on each day, the columns here, include information about ridership on that day, in the rider's total column, as well as weather factors such as wind speed, humidity, and the feels-like temperature, as well as two pieces of information about timing, so the day of the week and the season. Our analysis of any dataset will be guided by research questions. What we're working toward are multivariate research questions regarding the relationships among two or more variables. For example, how is ridership related to temperature, humidity, wind speed, day of the week, season, or even all of the above? Though those types of questions are our destination, it's also good to start with simpler and more direct univariate questions, that is, questions about one variable at a time. For example, ignoring weather and time of year, what general patterns do we observe in just ridership from day to day? In addressing univariate research questions, we'll start with visualizations or pictures. Visualizations can help us do a few things. 1, better understand the data and variables we're working with. 2, to inform our next steps, that is, help us determine what statistical tool or model is appropriate. And 3, to communicate our findings. We'll start with a categorical variable. The weathercat variable categorizes each day's weather into a category from category 1, pleasant, to category 3, severe. The most simple and powerful way to turn this lump of data into information about weather patterns is to construct a bar plot. Bar plots provide simple summaries of categorical variables. They simply count up and communicate how many cases or rows fall into each category. For example, we observe that category 1 weather here is the most common. More than 400 of our data points or observed days fell into this category. Category 3 has a much smaller bar, meaning category 3 weather is much more rare. And we often wish to follow up on visual summaries with more specific numerical summaries. In the case of categorical variables, a simple table of counts provides a quick option for specifying the bar plot information. Here, 463 days had category 1 weather and exactly 21 days had category 3 weather. Univariate summaries of quantitative variables get a bit trickier. For example, suppose we wanted to learn about the day-to-day bike ridership. To turn this pile of daily ridership numbers into information, we'll again start with visualizations. There are multiple approaches to visualizing quantitative variables, but we're going to focus on 3 approaches in this video. First, box plots or box and whiskers plots are one of the simpler options. These are built from only 5 pieces of information. First, to indicate the range in ridership, lines or whiskers are extended from the minimum to the maximum value. These communicate here that daily ridership ranges from roughly 0 rides to roughly 7,000 rides per day. Next, to indicate the typical ridership, a line is drawn at the median value or 50th percentile. This indicates that the typical ridership is slightly under 4,000 per day. Finally, a box is drawn to mark the middle 50% of the ridership values, from the 25th to the 75th percentile. This gives us a sense for the ridership on the most typical 50% of days. Here, the range is from roughly 2,500 to 4,750 rides. And this span from the 25th to the 75th percentile is called the interquartile range. Now, one pro of box plots is that they're pretty simple. Again, they're constructed from just 5 numbers. But that's also one of its drawbacks. It's a little too simple, and we can lose a lot of information in a box plot. We can get some of this information back with a histogram. First, histograms chop up the range of our variable into equal bins or pieces. Here, these pieces range from 0 to 7,000 in increments of 500. So the first bin is 0 to 500, then 500 to 1,000, then 1,000 to 1,500, then 1,500 to 2,000, and so on. Histograms then count up the number of cases, or days in this case, that fall into each bin. For example, notice that the bin ranging from 500 to 1,000 riders has a height of roughly 25. Thus, on roughly 25 days, we observed between 500 and 1,000 riders. And when we step back and check out the bigger picture, we build up our understanding of ridership. As shown in the box plot, notice that daily ridership ranges from roughly 0 per day to 7,000 per day. And the typical ridership is slightly under 4,000 per day. Further, notice that the shape is symmetric, as opposed to being skewed or uniform/flat. That is, ridership varies symmetrically around 4,000. Consider one last way of plotting this same data, density plots. Simply put, density plots are a smooth version of a histogram. When interpreting a density plot, it's important to focus on the big themes. For example, ignore the values on the y-axis. These don't mean anything on their own. Rather, they hold comparative meaning. Specifically, ridership values with higher density are more common. For example, the density curve is higher for values around 4,000 than for values around 0. Thus, we're more likely to observe around 4,000 riders than we are to observe around 0 riders per day. Further, the values on the y-axis are scaled so that the area under the curve is equal to 1, or it accounts for 100% of the variability in ridership. If you've taken calculus or probability, this might be a familiar concept, but if not, no problem. Finally, keeping this all in mind, we learn the same things from the density plot as we did from the histogram, summarized here. To summarize what we've learned in this video, when examining univariate visualizations, we want to pay attention to central tendency, that is, what's a typical value of the variable. We want to pay attention to the spread and variability, that is, how spread out are the values. Do they vary a lot or a little from case to case? What's the smallest, what's the biggest value? We also want to pay attention to shape. How are values distributed along the observed range? Is the distribution symmetric, right skewed, left skewed, bimodal, uniform, etc.? And finally, are there any outliers? That is, are there any values that are unusually large or small relative to the bulk of other values? Now, we didn't observe any outliers in this particular video or data set, but we surely will in future examples.